Hi, this is day 16, the derivative function continued. I'd like you to use this recording to try and get a handle on what's going on with day 16. Yesterday we talked about the derivative function and being able to get a generic form of the derivative function instead of just finding the value of the derivative at some number. As we've done in the past. So what I'd like to do is I'd like to look at a couple of examples of how do we find the derivative. So this first one, we're given f of x equals a quadratic equation. And on the last section of work we've done, I might have asked you to evaluate f prime at 2 using the definition of the derivative. And we started with the definition of the derivative, and we said, well, f prime at some value, and this time I'm going to say at x instead of at a, as I've done in the last unit, is equal to the limit of that difference quotient, f at whatever that x value is plus a little bit minus f at x all over x plus h minus that x, which just gives us the h, if we let h get really, really small, if we let the limit as h approaches 0. So instead of saying f prime at some number, f prime at 3 or f prime at 1, and plugging in the 1 where these x's are, or whatever value we're asked for f prime at, we're going to find this limit at f prime at any value x. So we're going to continue to have the limit as h approaches 0. But we're going to have, now this time I'm going to use this function, and wherever I've got an x, I'm going to plug in x plus h. So negative 4 parentheses x plus h squared plus 2 parentheses x plus h. And that's plugging in the x plus h into my f at x. And the minus f at x, which is the negative 4x squared plus 2x all over h. Now, if I want to evaluate this limit, I'd like this h to cancel out, because if I plug in a 0, I have a 0 in the denominator, the whole thing's undefined. So I'm going to need to expand this binomial, simplify algebraically, and see if I can get that h to disappear. If I can get it to cancel out, I'm in a good place. So let's go ahead and expand that binomial. I still have a limit as h goes to 0 is what I'm trying to evaluate. So I've got the negative 4 times x squared plus 2xh plus h squared plus 2x plus 2h distributing. And then over here, I'm going to switch colored pens. For the second bracket, I now have a plus 4x squared and minus 2x all over h. So I've got to distribute, I didn't close this parentheses last time, sorry. I've got to distribute that negative 4. And I have negative 4x squared minus 8xh minus 4h squared plus 2x plus 2h plus 4x squared minus 2x all over h. So the only thing I did on that line was distribute the negative 4 from this first parentheses. And if we look now, I've got a minus 4x squared, and I've got a plus 4x squared. I have a plus 2x and a minus 2x. So when I combine my like terms, I've got a negative, limit as h goes to 0, a negative 8xh minus 4h squared plus 2h all over h. Now I'm running a little low on space, so I'm going to bring it up here, equals the limit as h goes to 0. And I can factor out an h on the top, and I have negative 8x minus 4h plus 2 all over h, which is going to cancel, which gives me the limit as h goes to 0 of negative 8x minus 4h plus 2. And if I let h go to 0, that equals negative 8x plus 2. So f prime at x is equal to negative 8x plus 2. So if I wanted to evaluate what is f prime at 1, what is f prime at 7, what is f prime at 17, I could very easily plug into this new function, my derivative function, and evaluate each of these three easily without having to go back through this whole the limit thing, limit as h goes to 0, the difference quotient. So while this is long and complicated, it's better to do it once than to have to do it multiple times, unless you really enjoy doing that sort of thing. Okay, so on this example, we notice that this is not a nice polynomial function, the one that we've done in the past, the ones we've done in the past. So if I want to find the limit of f at x, and this time it's saying estimate at f prime at 2, instead of finding f prime at x, we're going to find that maybe that's not working out so well for us. If I look at trying to plug in f prime at x, I'm going to get stopped and I'm not going to be able to get something to cancel. So instead of f prime at x, I'm going to be looking at f prime at 2. So just as I did in the last section, limit h goes to 0 of f at 2 plus h minus f at 2 all over h. Definition of the derivative. So again, a limit as h goes to 0 of negative 2, just plugging into this function, negative 2 log 2 plus h plus 3. That's my f at 2 plus h, minus f at 2, negative 2 log 2 plus 3 is 5. All over h. Well, I'll tidy this up a little bit. I've got the limit as h goes to 0 of negative 2 log, well, I can say this is h plus 5 because I've got a 2 plus 3, and a negative minus a negative becomes a plus 2 log 5 all over h. Well, those h's are not going to cancel. I'm not going to be able to plug in my 0, evaluate algebraically. So instead of that, what I'm going to do is I'm going to go to my table of values. So table of values, I'm going to have, it's h that's going to 0. My y1, what I'm plugging into my calculator is right here. And the values I'm going to be looking for are a little bit to the left of 0, negative 0.1, negative 0.01, negative 0.001, 0.1, 0.01, and 0.001. Plugging that into my calculator, I'll let you go ahead and do that. We end up with values that approach negative 0.1737. So hopefully you got that on your calculator as well. So for this non-polynomial function, we have to just go ahead and plug in the value, the 2, so f at 2 plus h minus f at 2, because it's not going to fall apart nicely for us like the one above did. Okay, and a third way that we have to estimate a derivative is example C, where I'm not given a function at all. I'm just given the table of values, and this is the best we're going to do. So if I want f prime at 1, remember f prime, derivative, other word for derivative is, hopefully you all just said slope. So I'm looking for a slope. I'm looking for an average rate of change. So I'm going to find my average rate of change from 0 to 1. So from here to here, take my y minus y1 over my x minus x1, and I have 1 minus 0 over 1 minus 0 gives me 1. My average rate of change between 1 and 2 is 8 minus 1 over 2 minus 1 gives me 7, and then I'll average those. So I'm going to have my 1 plus 7 over 2, 8 over 2. My estimate of my derivative is 4. So this is not a terribly accurate way to find it, but given the information we have, that's the best we can do. Okay, example D. Find the equation of a tangent line. Okay, so we did that yesterday. We know, actually we've done it for a couple of days. We know if I want to write the equation of a line, find the equation of a line, I'm going to need a point. I'm going to need a slope. And then I'm going to use y minus y1 equals the slope x minus x1. Point slope form is the easiest one to use. So we're probably a little bit panicked because we see a trig function, but we're okay with that. So I want to know f at this pi over 4. So I'll plug that in. I'll have 3 cosine pi over 4 plus 2. And we've got to do just a little bit of a trig review here. If I want pi over 4, I know this distance is pi, so this must be pi over 2. So that must be pi over 4. So I see that this is a 45-degree angle, which makes this reference triangle an isosceles right triangle, 45, 45, 90, which means that each side of the triangle is root 2 over 2. If I want the cosine, I'm looking at the x value. So I'm going to take the x value, the root 2 over 2, and I'm going to come back here and I'm going to have 3 times root 2 over 2 plus 2. And if I wanted to tidy it up a little bit, I could say this is 3 root 2 over 2 plus 2 or plus 4 over 2 if I really wanted to get carried away. And I could say 3 root 2 plus 4 all over 2. And because I usually like to have the constant part first, I might make it into 4 plus 3 root 2 over 2. But I am getting a little carried away with doing that. Any one of these is fine. Then coming over to my slope, well, I need a derivative. So finding the slope, we need to find, let me bring this back down just a little bit so we can see it. F prime, where'd it go? Sorry about that. We need to find f prime at pi over 4. So we're going to go through the whole process that we've done before. We want the limit as h goes to 0 of f at pi over 4 plus a little bit h minus f at pi over 4 all over h. So this is not just a nice polynomial function, so we're anticipating that we're probably going to use a table of values, but we'll go through the process and simplify this as much as we can. Limit as h goes to 0 of 3 cosine pi over 4 plus h plus 2, simply plugging it into the function. I'll put that in brackets so you can see that that all goes together, minus f at pi over 4, which we just found over here. So let's put that in here as our, which form will I use? I'll use the easiest one. The 3 square root of 2 over 2 minus 2, plus 2, sorry. All over h. Tidying up, we've got the limit as h goes to 0 of 3 cosine pi over 4 plus h plus 2 minus 3 root 2 over 2 minus 2 all over h. And the limit as h goes to 0 of 3 cosine pi over 4 plus h, and then we have a plus 2 and a minus 2, so minus 3 root 2 over 2 all over h. And again, we're going to need to go to a table of values. So we're going to have h. We've got this as our y1. So be careful when you're plugging that in. Be sure that you put parentheses around this entire top. And we're going to have negative 0.1, negative 0.01, negative 0.001, because we're trying to approach 0, 0.001, 0.01, and 0.1. And we get this to approach, once we use our table of values on our calculator, approximately negative 2.12. So coming over to our equation of our line, that didn't work out as planned. We're going to have y minus, well, our y from over on the other side was that 4 plus 3 root 2 all over 2. Our slope that we just found, negative 2.12 times x minus pi over 4. Now what we might be able to do, because this 2.12, negative 2.12 is already an approximation, yes, we could approximate with that root 2 over 2 as well. So we could have y minus 4.12 equals negative 2.12 x minus pi over 4. And that leads back to the question of, couldn't I have just put this cosine pi over 4 into my calculator and get an approximate value over there? You could have, but we wouldn't have had the opportunity to do that nice trig review. We'll talk more about when do we have to use exact values and when are we allowed to approximate and use a calculator value. Certainly, whenever I ask for an exact value, then it means that I want the root 2 over 2 and not a calculator approximation. In this case, because we needed to use this table of values to get this approximation, we've already got an approximation in our equation, so a little bit more approximation isn't going to hurt us. Okay, a little review on evaluating limits. In this case, if I plug in the 2 in the denominator, I get a 0 in the denominator, undefined function, an indeterminate form of a limit. So, and I can't factor anything on the top, so I'm going to need to go to a table of values. I'd like you to try out that table of values. I think you'll find that they go to 2 different places. When I'm going to, my limit, my top is going to be going toward 2, my x value going toward 2. So I've got 1.9 on one end and 2.1 on the other end. Getting closer and closer. So 1.99, 1.999, 2.01, 2.001. I'll let you do the calculator approximation on your own. This is my y1. And I see that they go to 2 different places, so my limit does not exist. I'm, again, letting you do the calculator part on your own. For this one, can I just plug in a 3 in the denominator? Nope, get a 0, indeterminate form. So I try and factor. The top factor I'm going to factor out of 5. I've got x minus 3. And on the bottom, x plus 3, x minus 3. The common factors I can cancel out. So I'm now going to evaluate the limit as x goes to 3 of 5 over x plus 3. So I've got 5 over 6. So just a little reminder that limits don't always exist, and we can find these algebraically. Couple of little practice things I'd like to look at aside that are not on here is what happens when I expand a binomial. Remember that I've got x plus a times x plus a gives me x squared plus 2xa plus a squared. Well, what if that was cubed? Well, I'd start with my x plus a squared and then multiply by another x plus a. I'd like to, we know that this is already, this binomial expanded, this x squared plus 2xa plus a squared. And what I'd like to suggest is this vertical method of multiplication. Some of you have seen this, some of you will have not seen this. I like to put my binomial underneath the trinomial, and then when I multiply, I'm going to start with the first term on the bottom and multiply it by everything on the top. So x by x squared gives me x cubed. X by 2xa is going to give me 2x squared a, and the x by a is going to give me xa. Then I'm going to come to the second term in the bottom and multiply it by each thing in the top. So a by x squared gives me x squared a, and I'll put it underneath its like term. The a times 2xa is 2x a squared, which is okay, so hopefully you figured out where I buggered up, that this was supposed to have been an a squared, which would have made this an a squared. So when I am multiplying here, I've got x squared a. This is going to give me 2xa squared plus 2xa squared under its like term, and over here plus a cubed. So if we want to learn anything from my mistake, it's that when you try and hurry on these, you lose a detail and it buggers up the whole thing. So when I wrote this over, I missed carrying this a squared over. So now I can add my like terms. I've got x cubed plus now 3x squared a's and 3xa squareds and a cubed. If I had x plus a to the fourth, I could say I have x plus a squared times itself, which would be that x squared plus 2xa plus a squared times itself. So I'm taking the squared binomial, which I know what it is, and this time I'm not going to forget the squared on my a. And I'm going to use the same vertical method. If you're really good at the horizontal, just putting them next to each other and distributing, go ahead and do that. I generally lose terms when I do that. So x squared times x squared, x to the fourth. X squared here gives me 2x cubed a, and times my last term is an x squared a squared. Then I'm going to move to this next term. The 2xa times x squared is 2x cubed a, 4x squared a squared, and 2xa cubed. And then my last term, my a squared times x squared is another x squared a squared, and then 2xa cubed, and lastly an a to the fourth. Then I can add these all together. I've got my like terms lined up. X to the fourth plus 4x cubed a plus 6x squared a squared plus 4xa cubed plus a to the fourth. So these last three were just a little reminder from Algebra 2. Hope this helps.